So just going back, I would like to go with you over this question. So I'm asking you, how many stalls do we need between this instruction and the following one in case we don't have forwarding or in case we have forwarding? In case we have forwarding, we have an example exactly the same or very, very close to that. And we found that without forwarding, actually, there is no stalls at all. But let's go over it one more time with each other here, just like to remind you with how we should think about something like that. With this load word, at the end, I need the data to be written at the T1, which is basically the write back register. And if I would like the things to be written in the write back register, so this means that I have to wait, if there is no forwarding, just till the last cycle. Let's go over it one more time with you. I will fetch, decode, execute, memory, and then write back. With this guy, this T1 will appear here if there is no forwarding, correct? So my T1 will be available at the write back. With this store word, I am taking exactly the T1 and I would like to save it in a certain particular place inside the memory, correct? But I am taking exactly the T1. So if there is no forwarding at all, I have to wait till this moment that the T1 will be available. And only at this particular moment, I can take the T1 and move forward, yes, to store it to the memory. If this is the case, I have to assure that the decoding stage of this instruction is aligned with the write back of the load word. Or in another sense, the registers are aligned because write back is basically writing to the same register which I'm doing the decoding. So I would like to align the two registers. Because we mentioned also earlier by default, if I didn't mention otherwise, that I can write in the first half and then read in the second half, and all of this will be in the same clock cycle. If this is the case, I can just like align the W with the D here, and then write afterwards. So the F should be here, E should be here, M should be here, W should be here. If you look at this, so this means that I have two stalls. I have two stalls. Not three, I have two stalls. Why? Because if this is the case, and I have another one, of course, the next instruction, usually shifting one, correct? Because it will be the next I fetch after I finish. So D, E, M, W, if you have something like that, there is no stalls at all. And that's why I will not count this one. With this, I just like count the two, so I have two stalls. So this is if there is no forwarding, I have to wait until I found the W, and then I will align the D with the W, and I have two stalls. However, let's think that if there is forwarding, so F, D, E, M, W, I know that this guy, even though it is ready here, I know that at the output of the memory, I can actually grab the T1. If I can grab the T1 at this, so this means I need to think closely when I need the data of the store word. The store word is telling you, since the T1 is here, ready here, the store word is telling you, please save that T1, exactly one that you have here, in a certain particular place inside my register. Correct? In another sense, if this is my memory, and this is the T1 here, and appear at the output, I'm telling you, please take that T1 from the output, put it again to the input of the memory, but in another location by store word, correct? So I am forwarding from the output of the memory to the input of the memory. And that's why I will forward it from here to here, and then the memory should be in this particular stage, and just write the rest accordingly. If I write the rest accordingly, I found that there is no stalls, and the stalls basically are zero. There is no stalls at all, because what I will do, You just take the output of the memory, forward it, or feed the input of the memory. Okay? Let's take another one. We have now the add, and afterward we have the load word. We need to think again how many stalls without forwarding and with forwarding. If there is no forwarding, okay, so this add, again, F, D, E, M, W. There is no forwarding, again, the data is ready here. So basically the results of the addition at T0 will be available at this particular clock cycle or at this particular stage, correct? So here is the 0, T0. The load word is loading from that particular place to this. So I have to have the T0 ready from this guy. Yes? So I have to decode that correctly. If this is the case, and I will align the D here. So when I have the T0 available, I can decode it correctly. How many stalls? 2 stalls. Correct? Because I have to align the register. I will write at this clock cycle in the first half, and then I will read at this clock cycle, but in the second half. This is by default if I didn't mention otherwise. How about if there is forwarding? If there is forwarding, F, D, E, M, W. This is an addition. I would like to add this with this, put the results in T0. So the output actually of the ALU here will have the correct results if there is forward, correct? The output of the addition will be available at the output of the ALU. Is that correct? When I will need this, I am using the T0, so I will take the T0, save it in T1. Correct? But I have to add this to 8. Correct? So this means that when I feed my ALU in this, I have to feed the correct results. I need to feed the 8, which does not depend on any other instruction, but I need also to my ALU. I need to feed the 8, and also I need to feed the T0, and then I need to do the addition, correct? So the ALU need to get the correct T0. If the T0 is available here, and I can forward it from the ALU to the ALU, then what will be the rest? The rest here will be D, F, M, W. Correct? So if this is the case, again, I have 0 stalls if there is forward. So here is just like showed you the solution for all of the previous cases that we have solved together. Okay, this is just for your reference. Let's move to another question. The goal of the problem is to increase the execution speed of the code below by eliminating as many stalls and useless operations as possible. No operations in the branch delay slots. The code runs on a 5 stages pipeline MIPS CPU with forwarding. So remember that it is 5 with forwarding, with the characteristics discussed in lecture. Branch equal decision is in the ID stage. All of this is it's very useful information. Will help you solve the question. Note, branch delay slot is not hidden, meaning that no operation in the code below are always executed regardless of the branch decision. Indicate stalls in the code in the next slide with arrows right after the instruction where the stall occurs. I'm giving you the example here. If this is the code, and you think that there is a stall after this guy, just show me an arrow with a stall. So this means I do understand that you need a stall there. The following is not necessary to be correct. This is just an example. Okay, so there is forwarding. We have a 5-stage. The branch equal in the ID stage. And here is the code. And I'm asking you, how many cycles does it take to execute the entire code sequence below, including the stalls and the no-ops? And I'm assuming that I'm going through this code till here just one time. Please calculate how many clock cycles, including the no-ops, and if there is any stalls needed. Try to think about that. So with this code, if you look closely at this one, let's check between this and the branch equal. This is F, D, E, M, W. So this guy will write these things in the T0, correct? So this guy means that I have it finished here, because there is forwarding. Yes, I mentioned here with forwarding, as you can see, right? So if the data of the T0 is here, but the branch equal, we need the data when? We mentioned also in that question that the branch will do the comparison in the ID stage, correct? So this means that I can forward from the E to the D. So I have one stall here, correct? So I need one stall. So there is one stall here. Here there is no operation, and then load word the T0. Okay, again, if D, E, M, W, if there is forwarding, the T0 is available at the output of the memory, and the add will need that into the execution. So I can forward from the memory to the execution, and this is the case. Just write the rest. And that's why I have one stall, which is this one. In addition, of course, to this one. Between this load word and the add, it is the same between load word and add. So I don't have to rewrite it again. It's exactly the same thing. So I have here one more. Oh, this is store word. I'm writing to the T0. There is no dependence at all. Here I'm doing the C0s. There is no dependence at all. Here the C1, S1, there is no dependence at all. And so on and so forth. So this is the only 3 stalls. Okay, let's count. I told you that this will take 5 stages. Yes, so the first one will take 5. So 5, 6, the stall, yes? The stall will be 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 cycles. We have to begin with 5. Yes, because I'm telling you that with these stages, we have the washer, the dryer, and this and this. So the first one enter will take 5 stages. Anyone after that will just like take 1 stages afterwards. You cannot count that the first one will take 1 clock cycle. The first one to enter, just like to go with all of this, will take 5. Or anyone actually will take 5, but it will shift between one and the one afterwards by just 1. Correct? Assuming that you calculated all the stalls. And because of that, this is just 20, but we assumed that 19 can be correct if you didn't observe the stall between this and this, since at the time it was a common mistake. But I don't have to assume that it is correct, of course. It is not correct. It has to be 20. So assuming all stalls and no operation can be eliminated, how many cycles does the execution time decrease? Going back. So assuming that there is no operation, this is not there, this is not there, there is no stall here, there is no stall here, and there is no stall here. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Correct? So you can think like 4 or 5 less according if the previous answer was 19 or 20. Because of that, the total number, of course, will be 15 cycles. It can 4 or 5 depend on your previous answer if it was 19 and 20, and you detect the stall between the set less than and the branch equal or not. Let's switch the gear to another question. So here is with the branch prediction, I'm giving you the exact state machine, and I'm giving you the branch sequence. Branch sequence means while you are seeing like all of the branch in your code, one after the other, I'm telling you that the first one you will face, it is not taken. The second one that you are facing is taken. The following is not taken, and so on and so forth. And I'm giving you what is the beginning state, which state you will begin with. And then I'm asking you about your prediction, if this prediction was correct or not correct, and what is the state after. Just to remind you, as we mentioned earlier, with this state 0, 0 is completely not taken or strongly not taken. With the 0, 1 is weakly not taken. With the 1, 0 is weakly taken. With the 1, 1 is strongly taken. Another sense, this guy, I'm saying like he or she is completely not good, maybe not good, maybe good, extremely good. I'm going from the not good to the good gradually, or the other way around, as we described earlier. And they will move from the one to the others according to the same exact explanation as we had earlier. If I am in this not taken, if a not taken come, I will stay in the same. If a taken come, here of course, like need to put a T, I have to move to a one relaxation state. If another taken come, I will move to this state, and so on and so forth. And I'm telling you, I'm asking you just to fill the table. A question like that, I'm assuming that this is just like a present. Yes, and I'm not expecting that you will solve this incorrectly. Let's go over this with each other. So the state that you are in is 1, 0, so you are in this state. And then the branch that you face is not taken, so actually you went from this to this. What is the next state? 0, 1. So the state after is 0, 1. When you are in this 0, 1, what is your state? What is you, or what will your prediction be? Sorry, when you are at this state 1, 0, what is your prediction? Prediction is taken, correct? So my prediction is weakly taken, but at the end it is taken. Is this correct? You predict taken, but unfortunately you found that it is not taken. So your prediction was incorrect. Yes? You assumed or predicted that he is good, but unfortunately after you deal with him or her, you found that it is not good. So your prediction was not correct. And you move to this next state. Okay, so if this is the case, the 0, 1, this guy will move here. If I am at this state with the 0, 1, what is my prediction? Prediction means not taken, because in this 0, 1, I am at weakly not taken, or weakly bad, maybe bad, but I am still saying bad. However, the actually branch that you found that it is taken, you found the branch is good. So your prediction was incorrect. But you was here and taken come, you actually move to this 1, 0 is the next state. And so on and so forth. So I don't have to go over all of this with you here, but I'm assuming that you already understood the concept. Okay? Is this clear? Let's move to the next question. Examine the function prototype and MIPS implementation below, and I'm giving you the function which multiply power of 2. I'm giving you the 2 arguments, and I'm expecting that you by default know that this is A0, and you know by default that this is A1. I don't need to give you this information. We are using 5-stage MIPS pipeline data path with separate instruction and data that can read and write to registers in a single cycle. All of this information, as we have covered earlier, we have an instruction memory separate from the data memory. We can write in the first half of the cycle. We can read in the second half of the cycle. So basically in one single cycle, I can write and read. Assume no other optimizations, meaning no forwarding, no branch prediction, etc. Nothing. The default behavior is stall when necessary. Branch checking, this is a new information, is done in the execution stage. This is a new information. Earlier, we have covered if we are in the ID stage, comparator, and then, or if we have in the memory stage. With this one, I'm telling you that the execution, the results of the branch equal is at the execution stage. So I know the results at the execution stage. Given all of these, and given that this guy, the POW, is equal to 1. I'm telling you that POW is equal to 1. How many stalls do I need and how many cycles do I need in order to execute that particular code? So here is just like the code, and we would like to go over it one more time to see how many stalls do we need until we see like how many clock cycles. So the load word at the very beginning, F, D, E, M, W, as we expect. With the next one, the branch, as you can see from this, there is no dependence at all between line 2 and line 1, correct? There's no dependence at all. So that means that just with this branch, I will just write the F, D, E, M, W. So at this particular stage, the execution, I will know the results of the fetch, of the branch. This gives me an indication that I cannot fetch the next instruction unless I know the results of the branch. And this results is only known at the execution cycle. So after the execution cycle, I should be able to fetch correctly. So this means that with this guy, I will fetch it correctly only after this. So F, T, E, M, W. And because of that, I have 2 stalls. Correct? Let's see between the shift and the addition. Between the shift and the addition, as you can see, the shift is writing to the V0. The addition is doing with the A1. Yes, there is nothing, there is no dependence, so there is no stall at all. I have just the F like that. Correct? Then the addition and the store word. Store word is store word V0, yes? Store word V0. So this means that I have to assure that V0 is correctly available before I store it. If you look at number 3, you will find that this V0 is available when? This V0 should be available here if there is no forwarding. Correct? And because of that, with this store, I have to assure, since it is available here, and there is no forwarding at all, I have to assure that when I store word the V0 in the decoding stage, it is aligned with this stage. Correct? Because I will write the V0, and then I will read the V0. Correct? So I have to make sure that the D is available there. And because of that, just write this F. Then I have 1 stall. F, D, E, M, W. And then after that, I have the jump. The jump, there is no relation at all. It's just like jump loop. There's no relation at all between this and the previous one. So F is here. Correct? But we mentioned in class that after the jump, I have to wait at least 1 no operation. So I have to stall 1 time after the jump. And after the jump, because of that, this guy, I have to wait for 1, so it will be here, D, E, M, W. And we earlier mentioned that between the branch and the following instruction, I will know the results only at this execution. And I can fetch the correct instruction afterward, only afterward. So I will finish here at this clock cycle. If you count, this is cycle 18. Okay? This guy here is totally important, extremely important, that guy to be aligned with this guy. This is extremely important, because otherwise I will not be able to get the correct V0. So you can see this here, solve it, and you see like the 18 cycles with the whole code written here. So when you solve it by yourself, you can easily go over it one more time. Again, the most important things is to see like how is the flow of the codes one after the others. We are at the very beginning, load word V0 with the A0. A0 is the first arguments. I don't care about what is exactly the value of this. With this branch equal, the A1, I'm checking if the A1 is equal to 0 or not. But I'm telling you in that question that POW is basically equal to 1. This POW is equal to 1. And POW, if you look at the code, you will find that basically A1, the first argument, is equal to 1. So the first time I'm looping, if I'm checking if A1, which is equal to 1, equal to 0 or not, of course it is not equal. If it is not equal, so I'm not going to that guy. I'm just taking the next instruction at the shift left, correct? And again, shift left to the V0, and then with this guy, I am decrementing this A1 by 1. So after this, actually my A1 is equal to 0. I will store word that value and then jump the loop. I go to this loop. Going to this loop, but with A1 is equal to 0. So if I check if it is equal to 0 or not, I found that it is equal to 0. And that's why now I have to go to the exit with the jump register. As you can see from here, after the branch, I have the jump register. And of course, after jump register, I'm just finishing my function. And I went through all of these stalls needed as we described in class earlier. Let's take another question. Consider the 5-stage single issued pipeline MIPS data path consisting of instruction fetch, decoding, execute, memory, write back, as we mentioned earlier. I'm giving you the value of the S0, S1, S2, S3 like that. I'm giving you also the values of T0, T1, T2, T3, T4 with all 7. And then I'm giving you this code. I'm giving you the addition, then AND, OR, sub, and shift, and so on. And then I am asking you, starting numbering the cycles with 1 when the add instruction enters the IF stage. From part 1 to 3, assume that the data path is broken and there is no forwarding and no stalling. What are the values of T0 to T4 at the end of cycle 7? So with this one, in order to think about and see like how many cycles and so on and so forth, again, let's begin with here with the all of these F, sorry, F, D, E, M, W. And then we said that there is no stall, there is no forward, there is not, I mean, just like F, D, E, M, W, F, D, E, M, W, F, D, E, M, W, F, D, E, M, W. And with the very beginning with adding the T0 to the S0 and so on and so forth. This guy will be ready only at this stage, correct? At clock cycle 5. At clock cycle 5, this T0 will be equal to S0 plus 0. So basically T0 is equal to S0 plus 0. If you look at the previous table, you will find that this is equal to 56. 56 plus 0. Try to see the second one. The second one, again with this AND, the results will be available only at this stage, which is clock cycle 5. Correct? What exactly that? It is just ANDing the T0 with S1, put the results in T1. So basically T1 is equal to the T0 ANDed with S1. In another sense, you are adding the value of 7 with 30. If you do this, you will find that it is equal to 6. Why? Because if you would like to write 30, this is 1, 1, 1, 1, 0. If you would like to write 7, it is 1, 1, 1, and all of this is zeros. If you would like to do the addition, the AND, so this will give 0, 1, 1, 0, 0. And this is 6. Correct? So the value here is 6. With this OR, I'm ORing T0 with S2, put the results in T2. Okay, so T2 is equal to T0 ORed with S2. T0 is equal to what? 7 as given in the table or in the previous slide, or this T0, updated T0. This is the trick here. With this guy, I am doing the stuff before I updated the T0. And because of that, it will take the old value of the T0. And that's why this will be simply 7 ORed with 30. And if you do the ORing, it will give you 31. Because basically, if you OR this with this, the ORing here, 1 or 0 will give you 1, 1, 1, 1, 1, which is basically 31. This value is 31. Correct? And then the subtract will take the T3 is equal to T0 minus S3. But now the T0 has been updated. And then it is equal to 56 minus 7, which is equal to 49. Correct? And then the last one with the shift. Shift right means I am dividing by 4. So basically with this guy, T4 is equal to T0 divided by 4. If you do that, you will find that this is equal to 14. Correct? The most important thing is to see when the data is ready and if it will calculate the correct results or it's just like whatever you had earlier from the initial values. This is the most important things here. So if I'm asking you about cycle 5, you need to know like what's exactly at cycle 5. If I'm asking you about cycle 6, what's exactly the correct results at cycle 6, what will be the correct result at 7, and what will be the correct results according to all of these things. So as you can see from here, we're just like asking the questions with all of these stuff. You find that this is the correct value. With this one, you will find also that this is the correct, and with this one was the correct. So all of the answers are C, and I have proved why they are equal to that as we have seen in the previous slides.